Hello, today I will present you about my paper, We Mind Your Well-Being, Preventing Depression in Uncertain Social Networks by Sequential Interventions. This problem is becoming a major concern as depression and mood disorders are increasing nowadays, and also counseling services both in community, university, and workplaces are emerging to help if there is someone in need. However, there are a few challenges for providing counseling in university contexts. First, there is only 6 to 7% of the students who seek for counseling, although there are much more students that can be struggling with stress and depression related issues, as well as there is limitations in capacity of universities. According to a survey, there is only a ratio of 2,700 students per counselor in large universities. Thus, the solution is to choose the students with high consent to provide counseling. With this approach, we encounter one more challenge. That is, the university counseling centers cannot obtain complete information about students' mental states and the relationship between them at the beginning of the intervention. So, how can we improve to effectively provide the counseling to students? To address this problem, we first consider the complete motivation scenario of universities' counseling centers conducting a series of interventions where it has the initial estimation of student mental states and influence. Given this scenario, we will optimally plan the sequential interventions in an uncertain network to invite students for counseling. We will also use reasoning to predict students' mental states as we collect more information. Before I present the proposed model and the solution approach of the problem, let me provide some background that are necessary for the model. The first topic is influence maximization. There are two basic diffusion models, independent cascade model and the linear threshold model. The next related work to our problem is partially observable Markov decision processes to formulate problems with uncertainties. Formally, it is defined as shown in figure. With these backgrounds, I will explain the model that we propose for the problem. First, we present the student network with a graph where we represent the students as nodes and the edges as influence between the students. Since the influence the students have on each other can be different, we represent the edges as bidirectional. The mental state of the students are presented with node values from a discrete set, where 0 is the happiest state and the mu is the most stressed state. We represent the influence with the edge weights from 0 to 1. In such student networks, we consider the emotion propagation, where a student mental state can affect others both positively and negatively. For example, with a network of 5 students, we can consider that if we choose student 3 for counseling, the mental state of his friends 4 and 5 might also improve due to the positive effect of counseling received by student 3. For such emotion propagation, we propose a model considering the psychological studies and the network behavior. In propagation model, we consider the change by the intervention and the change by the emotion spread from friends. And the emotion spread is modeled as the relative value of emotion spread from one of the students with the emotion spread from all the neighbors. Next, we formulate the problem as POMDP. To do that, we must first consider the uncertainties of the problem. For the mental states and influence, we define two matrices for the initial estimates, head B and head W accordingly. As we conduct each intervention, head B and head W are updated. After emotion propagation model and uncertainties are considered, we formulate the POMDP accordingly. States, action, observation, observation probability, transition probability, reward, history, policy, and the expected reward for our objective, which is to find the optimal policy that will give the maximum expected reward. And the last as belief. The belief is obtained by the estimated matrices and updated after each action. With the updated belief, we can also update the estimates, which are head B and head W. To solve the formulated POMDP, we propose MLPRAP, where we first solve the POMDP with QMDP heuristic POMDP solver and added the reasoning to predict the student mental state from collected information in each step to make up for the loss of solution quality due to uncertainties. Also, the abstraction of POMDP states as well as multi-level partitioning of the student network to improve scalability so that sequential interventions can be planned for large student networks. For reasoning, we consider the following model. At each event of intervention process, we can consider that the value of mental state of each student is changed. In this case, we can also consider that the student mental state has been constantly affected by other events before the start of interventions too. Hence, we first define the state relationship rule accordingly. Using the rule, the reasoning process steps from the student I, which we just intervened, and her friends K, L, and J. Using this information, we can predict the mental states of K, L, and J shown in green. Using the values in green, we again estimate the values of I. If the estimated values are out of the range for I, we discard the values from the predicted range. Thus, we finally get the newly adjusted range as shown in blue. To solve the larger networks, we first try the abstraction to reduce the number of states in the state set. We define sigma to define an abstracted discrete set to represent the mental states. An example of sigma as 2 is shown here. We also propose the multi-level partitions to further scale up. The first method is the balanced partitioning. For example of eta as 2 and k as 3, we partition the network into 6 partitions. And then we ensemble the POMDPs and compute best one node action. Only then we choose best 3 node action to have an action of 3 students to intervene. The second method is cluster partitioning. This is to prevent the information loss due to the link breaks in balanced partitioning, where we cluster first and break into subpartitions if the constant L here exceeds the limit. After applying all the techniques to solve the formulated POMDP, we evaluated the results on synthetic networks against degree centrality algorithm and Hill algorithm. Using these two baselines, we compare our MLPRAP balance and MLPRAP clustered. We saw significant improvement in terms of scalability as well as in terms of solution quality. Also, we observed the same trend in the real-world networks. In conclusion, for effective counseling in large network, we consider the network dynamics, emotion propagation model, and the POMDP formulation to address the uncertainties. Also, for solving the POMDP with large networks, we apply reasoning, abstraction of states, and multi-level partitioning of graphs to increase the scalability while maintaining the solution quality. Thank you very much for listening to my presentation. My contact information is as shown here. Thank you.